Hello everyone, welcome to my second lecture on embedded systems. So as we have seen before, here is the definition of embedded system. So any device that includes a computer but is not itself a general purpose computer is called an embedded system, like your mobile phone or an ATM machine. Okay, so hardware and software part of some larger systems and expect to function without human intervention. Okay, like some robot, automated robot, anything that needs a brain to operate on its own. Okay, to do some work for humans is called embedded system. So its main functions are to respond, monitor, control external environment using sensor and actuators. So sensors sense the external environment and actuator actuate it. Okay, so here is the general architecture of the embedded system. So on one hand we have sensors, okay, and after getting inputs from the sensors we are conditioning the sensor, the input voltage or current, whatever it is, and feeding it to the microcontroller. Okay, and the microcontroller, after calculating the inputs, produces output, and those outputs actuate the actuators, give signals to the actuators, and the actuators control the system for which the embedded system is employed. Okay, so here are some examples of embedded systems, like personal digital assistants. These days these are very rare, so it is most probably you have not seen any of them. And next is printer, cell phone, automobile. So these days the cars or other automobiles includes lots and lots of embedded system like microprocessor and controller, etc. It is an engine, in brakes, in dashboard, etc. So television in your home or set-top box, it also includes microprocessor and it's an embedded system. Your household appliances like micro oven, your washing machine, all these machines have processor in it. Okay, so these are the example of embedded system. And your surveillance system. So surveillance system are for security purpose, like camera outside your home which is connected to your computer. Okay, or some surveillance system directly feed into your mobile phone. So these are the examples. So here is an example of another embedded system, that is NASA's Mars SOJOURNER rover. Okay, it was used by NASA for its Mars mission, and it uses 8-bit Intel 80C855 processor. Okay, next we have GPS receiver in automobile or handheld GPS receiver. These receivers have 16-bit microprocessor inside it. Next we have S1 MP3 player. So this MP3 player have Z80 compatible processor plus 24-bit digital signal processor, that is DSP. So Z80 compatible processors are generally 8-bit processors. Okay, so it is an example of an embedded system which have one general purpose processor plus one DSP, digital signal processor. Okay, 24-bit digital signal processor. Here DSP doesn't mean digital signal processing as one of the subjects, but it is digital signal processor. Next we have Philips portable DVD player. Okay, back in days this used to be popular, but after the introduction of smart gadgets, these products have been obsolete. But here is an example. includes 32-bit RISC processor. Okay, so what is RISC processor? Reduced instruction set computer processor. Okay, so why it is reduced instruction set? Because it is made less complex by reducing the number of instructions. Okay, so this is 32-bit. Next we have a very popular one, Sony AIBO robot dog. These are robot dogs, very popular in Japan, and this is latest model ERS 1000, and it includes 64-bit quad-core processor. Why? Because simultaneously it has to sense external environment, understand it, and respond to it according to its program. Okay, so these are quite advanced robots. So here are characteristics of embedded system. First one is sophisticated functionality. So the embedded system must be sophisticated. Second, real-time operation. Okay, so when the user is interacting with the embedded system, it has to execute some real-time operations. Okay, so low manufacturing cost. So for mass production, the cost of the system must be low, otherwise people won't buy it and it will be obsolete. Then we have application dependent processor. So other than general purpose processors, we have application dependent processor which are made exclusively for certain applications. Okay, next we have restricted memory. So memory is another thing that is very important in designing embedded system. Okay, because first, memory cost more money. Okay, so a lots of memory would not be economic, so we have to choose instruction set or processor which use low, like small number of instruction. Okay, and we have to make those program smarter so that the size of the program is low but it does the same job. Next we have low power. So power consumption is critical in battery powered devices. Okay, because first we have some limitation because of the size of the battery, size of the embedded system. Okay, so the less the power will be, the device will run more on a single charge. Okay, next we have excessive power consumption increases system cost even in well powered devices. Okay, so if certain device consume excessive power, okay, then we have to charge it more often and that will increase the cost. Okay, and alongside that we have cooling cost, designing systems for cooling the processor, because more power consumption means more wattage and more wattage mean more heat. So we have to design the system in such a way that it consume low power. Okay, so that it decreases the cooling system cost as well. Next we have manufacturing cost. So manufacturing cost has different components. Okay, first we have non-recurring engineering cost for design and development. Suppose you have some embedded system that does certain works. Okay, so first we have to design that system for that specific application. Okay, so that is called non-recurring, because in non-recurring, recurring means happening again and again. Okay, so the first cost is called non-recurring engineering cost for designing and development that product. Second, we have cost of production and marketing each unit. So the production and marketing cost is what? Suppose you have a flight control system. Okay, so you want to design the control system which will increase the efficiency of the flight. Okay, so the non-recurring engineering cost, you can invest more, but if you want to design a mobile that you want to introduce in the market for consumers, okay, so in that case you have to keep in mind the cost of the production as well, because no one will buy it if the cost is very high. So best technology choice will depend on the number of units we plan to produce. Okay, so for mass marketing, for mass markets, the cost of production generally reduces because we are implementing machines which are doing same work again and again. But suppose we want 1 unit or 2 units of certain embedded systems, then the non-recurring engineering cost increases. Okay, so real-time operation. So real-time operation is important for embedded system. So there are two type of real-time. First is hard real-time and soft real-time. So systems must finish their operation by certain deadlines. So what is hard real-time and what is soft real-time? Hard real-time mean missing deadline causes failure, and soft real-time mean missing deadline results in degraded performance. Suppose there is a nuclear reactor and the embedded system is the cooling system of the nuclear reactor. So what happens if the cooling system misses its deadline and is unable to control the heat? So the nuclear reactor, that would be catastrophic. Okay, the output would be catastrophic. The whole system could burst and it could be fatal. But suppose you are playing a video and the video decoder is unable to decode one frame. Okay, so that would make the video output a little degraded. Okay, so here that's why I have written degraded performance, because that is soft real time. Okay, so hard real time operation and soft real time operation. Next we have, so many systems are multi-rate, must handle operation at wide variety rates. Okay, so a single system can include embedded systems with hard real-time operation and soft real-time operation as well. Okay, so application dependent requirements. First is fault tolerance. Okay, what is fault tolerance? Like when you are designing a system, there are some moments where fault occurs. Okay, we try to minimize it. It is ideally fault for the system there should be no fault in the system, but that is not the case. Okay, and in that case, when the fault occurs, the system should be able to tolerate that fault. Okay, so the system should continue to operate despite hardware or software faults. Like suddenly your phone battery is low. Okay, so it cannot just turn off without saying anything or displaying anything. Okay, suppose you are doing some important work in your mobile phone or computer, and not computer but laptops, battery powered laptops. Okay, and suddenly the whole system turned off, so your unsaved work would be lost. Okay, so you have to display, the system has to display some warning or anything so that the user can prepare for those faults. And the system, even this is one case, but in other cases, suppose there is software faults, like software fails to run some part of its applications. Okay, so the whole system should not crash, but it should have the level of tolerance, some level of tolerance of these faults. Second, safe. System should avoid physical or economic damage to personal property. So the embedded system, if fault occurs, even if the fault occurs, it should be safe to the user. Okay, it should not do any harm to the user or property of the user. Alright, so what are the more features? Dedicated systems predefined functionality according to hardware and software design. Next, programmability rarely used during lifetime of the system. What is this? This means, suppose, like, most of the time what happens, you design a embedded system and you have to test it for it determining its faults, because the users might not be tech savvy. Okay, so suppose you have bug in the OS, okay, and you are thinking of updating that bug, okay, in the next update, okay, but the user might not be tech savvy, so he would not update the operating system, so he will continue to run the previously installed system, which might have some bugs which are faulty, bugs are generally faulty, but the bugs is such that it is unable to run the system smoothly. Okay, so because once the system is made, it is not reprogrammed generally, so we have to keep that in mind when designing an embedded system. Okay, and we have real time, fault tolerant and safe. So what is real time? Real time means, suppose the embedded system has to do some work, so it should do that work in the exact time it was supposed to. Okay, if the same system does some work after 5 minutes or 10 minutes, it might not be relevant. Suppose, for example, you are withdrawing some money from ATM and you punched your card, debit card or ATM card, and entered your PIN, then selected the amount of cash you want to withdraw, but the money is coming after 1 hour, and by that time you would be gone. Okay, so any other person, the next person will get the money. So this is an example of real-time operations. Okay, and this is called, the system must be temporal, because temporally correct. We'll see that next. So what are the types of embedded system? So there are different types of embedded system. One is similar to general computing, like, okay, so that should not be PDF but PDA. Next, video games. Video games are looks like general computers. Okay, and even in some computers, most of the computer we can play video games, but video games looks like general computing. Another one is set-top box, ATM machines. And other type of embedded system is control system, systems that are controlling some work via feedback in real-time operation, like flight control. Okay, so you have set the angle or the elevation. Suppose you want to go a bit higher, 1 meter higher in aeroplane, so you have set the flight control system so that it goes 1 meter higher. Okay, so it would generally do feedback of its output to see if it has reached 1 meter higher or not, and it would continue to give input, which is the difference, which is the error, the difference between input and the required output. Okay, the actual output and required output. So control systems like vehicle engines, okay, nuclear reactor. Suppose in nuclear reactor you have to keep the temperature at certain levels. Okay, so we do that with the help of control systems. Okay, there is a sensing element in nuclear reactor that senses the temperature, and once the temperature is higher than expected, it cool down the system until the desired temperature is reached. Okay, next we have signal processing. So devices like radar, sonar, DPLR, these are signal processing devices. Okay, this embedded system processes signal. Okay, so DVD player process audio and video signals. Okay, things like that. Next we have communication and networking. So cell phone that we use, internet appliances, these are communication and networking devices. So Google Home, Amazon Alexa, these are embedded system. Okay. So nature of system functions. So first is, what are the nature systems of the functions of an embedded system. One is control law that we have seen before. Next is sequencing logic. So if this then that, like if this happens then system will do something, okay, otherwise it will do any other thing. Next is signal processing. Next, application specific interfacing and fault response. So here I have given a expanded architecture. We have seen the architecture before, but here we have expanded that architecture. Okay. So here we have CPU. Okay. And with CPU we have memory. And with CPU we have analog to digital computer converter or ADC, digital to analog converter or DAC or DAC. Okay, we have sensor to sense the external environment, actuator to actuate the input. Okay, and in memory we have software, the operating system and the application software, FPGA and ASIC. So what is this? Application specific computer. Okay. So what will ASIC do? We will insert some digital logic inside FPGA or ASIC, and we can use it alongside low power, lower bit CPU. Okay. Next we have user interface. User interface is a must, because otherwise how will the user sorry for that. So user interface is important, because otherwise how will user set what it desire. Okay. So suppose there is a temperature controller sensor and the user want to set some predetermined temperature for the room. Okay, suppose your AC. Okay, so you want the temperature to be 25 degrees C. So there must be some user interface. Okay. Next we have diagnostic tool. Okay. So what is a diagnostic tool? So diagnostic tool is something that diagnoses whether all the parts of the system is running properly or not. Every system must have one diagnostic tool, first for the user, and secondly so that before starting a system it is able to diagnose whether everything is okay or not. Otherwise, in some cases it can create catastrophic failure, and also it helps the user to determine the fault. Okay. So apart from that we have auxiliary power management like cooling system and other things, and actuator is changing the sensor using feedback, and casing. So what is casing? Casing means external casing of the embedded system. So suppose we have a brilliant embedded system that is operating fabulously, but the casing is bad. So what happens? Because of the environment the embedded system fails, because the casing was not hard enough, okay, or good enough for the environment. So casing of this embedded system must be determined depending on the environment it would be. Okay. So suppose the embedded system will be on a system which always vibrate, okay, or faces a lots of oscillation, okay. So we have to design that system, that casing, in such a way that it can withstand the environment, okay. So here we have hardware evolution of embedded system, what it was and what it is now from top to bottom. So first we had general purpose microprocessor and microcontroller after introduction of what? MOSFET. So at first there was MOSFET was invented, and after that we started the minimizing those sizes, like with the help of Moore's law. According to Moore, the size of the integrated transistor would double in 1.5 or 2 years. Every 2 years the amount of transistor we have on a single chip will be double, okay. Next we had DSP, digital signal processors, okay, and this processor processes digital signals. Next, and so we are going from in this way, we are going in a timeline. So what happened previously and what is happening now, okay. So next we have application specific processors, some processors which are not general purpose but are only made for some specific application. And next, this is the current trend, systems on chip. So the mobile phone you are using, okay, or notebooks we are using today, digital notebooks, all are system on chip. So what is system on chip? We have microprocessor, alongside that we have some application specific processor, okay, input, output, memory and other peripherals in single chip, okay. So this is the current trend. Next we have implementing the embedded system. So how we can implement the embedded system? So first is hardware implementation, next is software implementation. So one important part is processing element, okay. So we have to select the processing element according to the requirement of the embedded system. Next, peripherals mean input and output devices, okay, like this might be other than general purpose standard input output devices like keyboard and mouse. There can be other input and output devices, okay. Next we have interfacing sensor and actuators that will sense the environment and actuate the system, and interfacing protocols, okay. So interfacing sensors means like it can be many things. Interfacing sensors means like input and output devices mean the touch screen you are using, okay. And interfacing sensors mean suppose you have to sense and control the output temperature, okay. So the temperature sensor is the interfacing sensor, and actuator is the part of the motor, that is the motor compressor, okay. So the voltage to the motor compressor would vary according to the temperature it senses. Next we have memory. So memory means RAM and ROM, read only memory and random access memory. Bus means system bus and etc. And next we have software. So there is system software and application. System software means suppose OS. So suppose you have a laser printer and you have another, suppose, copy machine, okay. So it might be possible that both this system is using the same system software or OS, okay, but are running different applications, alright. So this is possible. So in case of software, the programs must be logically and temporally correct. So logically correct we can understand, but what is temporally correct? Temporal mean that deals with time. So as I said before, the system must be temporarily correct. Like I have given example before, like suppose you are withdrawing money from ATM, so ATM is embedded system and it disposes your money after 1 hour, so that would be of no value. Alright, next it must deal with inherent physical concurrency, reactive system. So what is physical concurrency? Physical concurrency means several things is happening simultaneously. Okay, so embedded system, because the world, our real world, happens concurrently. Okay, so suppose there is a temperature controller, okay, and the system has to sense the external temperature, and concurrently the user might be setting up the temperature which it should be. Okay, so there are multiple works that the system is doing. This is called concurrency. Okay, reliability and fault tolerance. So the system must be reliable. Okay, otherwise the system won't use it, because there is a low possibility that it will succeed. Suppose if the ATM machines that we use generally were not reliable, suppose the money would not be disposed 50% of the time, there was a possibility, then what will happen? People won't go to ATM machines. Other than that, they will go to banks, because if they sign the withdraw form, they will get the money for sure, but the reliability of the ATM machine is 50%. Okay, and fault tolerance are critical. Fault tolerance means I have discussed before. Okay, so application specific and single purpose. Okay, so the software that today's systems use, the embedded systems use, are application specific. The OS might be same for different system, but the software they use might be different and designed and created for that single purpose. So multitasking and concurrency. Embedded system need to deal with several inputs and output and multiple events occurring independently at the same time concurrently. Okay, so separating tasks simplifies programming, but requires somehow switching back and forth among different tasks, that is multitasking. So the system is a kernel to switch back and forth. Okay, like in mobile phone we have that switch which would show us all the window that is open, or in mobile or in Windows system we have task manager that show all the system that is running right now. Okay, so we need such type of program that can handle that separating task and multitasking. And concurrency is the appearance of simultaneous execution of multiple tasks. Okay, so here is an example of concurrency and temperature controller. So when temperature controller is monitoring a temperature, simultaneously it is monitoring time of the day. Why it is monitoring time of the day? Because previously the user has said that for in the morning time the temperature should be like 25 degrees C. In like between 10 a.m. and 4 p.m. the temperature would be say 21 degrees C, and for night time or evening time it will be something else. So the temperature controller has to monitor the time of the day. Okay, and alongside concurrently he has to monitor the temperature with the help of sensors, and it had to monitor the keypad, because the user might be setting some changing the system, the previously mentioned time of the day. Okay, customizing the system, so you have to monitor all the things concurrently. So concurrency in embedded system is important, and the OS and the processor should be such that it can handle the concurrency. Okay, so what are the challenges in embedded system design? First, how much hardware do we need? Okay, so hardware means processor, how much processing power you need, and size of the memory. Okay, so do we need an 8-bit processor or a 16-bit processor, 64-bit processor, single core, dual core, quad core, octa core. Okay, what CPU do we need? Because with increasing word size of the CPU, the price of the CPU goes up as well, and it will increase the device cost. Next, we have size of the memory, because more memory means more power consumption and higher price, but lower memory can degrade the system performance. Okay, you should have known that low power mobile phones with low RAMs. What happens in mobile phone in low RAMs? It hangs. Okay, so next we have, how do we meet our deadlines, like faster hardware or cleverer software. So to meet a deadline, whether it is real, deadline means what? That at a certain time we have to execute a certain task. Okay, and so what we will do, we will design a cleverer software that will do that work cleverly, or a faster hardware that will do that work faster. Okay, suppose that there is a long instruction, like long calculation in the system. So should we buy or implement with a 64 bits microprocessor, or we would design the software in such a way that it takes lesser steps to execute that program. Okay, so actually in reality the solution is a bit of both. Okay, we have to compromise between faster hardware and cleverer software in designing an embedded system. So next, how do we minimize power? Okay, so first we have to turn off unnecessary logic, reduce memory access, because memory access means more power. Okay, so these are the challenges in embedded system. So here is a whole picture of the embedded system design. So embedded system design is multi-objective, multi-discipline, and these are the components of the life cycle. So multi-objective means, what are the objective of designing an embedded system? Dependability, it should be dependable, it should be affordable, it should be safe, secure, scalable and timely. These are the objective of the designing the embedded system. Okay, and this design can be multidisciplinary. It can be electronic, software, mechanical, control algorithm, human, society, medical, biomedical, chemical. Okay, so these are the discipline that an embedded system can have. Okay, like body glucometer, like that diabetes patients, diabetic patient use that meter that determine their blood glucose. Okay, so that is chemistry. Okay, so we are interacting with electronic plus chemistry. Okay, there are robots. So robots are electronics plus electrical, because of the motor, and mechanical. Okay, because of the other parts that is moving. So it is multidisciplinary, and the life cycle is, first we have to. So what is the life cycle of embedded system design? So first, for designing an embedded system, we have to look at the requirements, we have to design, we have to manufacture, we have to deploy, we have to see at the logistics. Okay, how the embedded system is performing, and retirement. So what is retirement? Retirement means, suppose you designed an embedded system, but you do not support it after 1 year. So the people that have put faith on you, okay, so they will be devastated, because suppose you produce a certain brand of mobile, certain number, like anything, okay, mobile X, and after 1 year you stop supporting it and you stop creating its parts. Okay, so suppose the user broke the mobile phone, okay, and need to replace certain component of the mobile. but you are no longer producing it. Okay, so the user have to buy a new system, other system. Okay, so that is, you have to plan the retirement, how much time you will support the software, and then you will withdraw supporting it with the introduction of newer systems. Okay, so what are the design goals? First is performance, that is overall speed and deadline. Next is functionality and user interface. It should be smooth, it should be user friendly, it should be functional, it should have good speed, and it should meet deadlines. Manufacturing cost, okay, that is NRE cost. NRE cost means non-recurring engineering cost. And production cost. Next we have power consumption. We have to minimize the power consumption and other requirements like physical size, like we cannot create a mobile phone with 1 kilowatt of weight, nobody will buy it. Okay, so what are the functional versus non-functional requirement? Functional requirement means output as a function of input. So for what purpose this machine is being created, and if this machine is performing that function well. And the non-functional requirements are time required to compute the output. So the system is functional because it is producing the output we are creating the system for, but the time required is more. So this is not functional requirement, but this is necessary. So this is non-functional requirement. The size, the weight, the power consumption, reliability, these are the non-functional requirement of an embedded system. So what is the steps in the design and development? First is requirement, second specification, next architecture, then component design, then system integration, then testing. Okay, we have to test the system so that we can determine its faults and rectify it. Okay, so should we use top down or bottom up procedure, bottom up design in designing embedded system? We can use both. Okay, in top down design mean we will start from the abstract description, okay, what the system will do, what is necessary, then we will specify the most detail like what CPU will be used. Or we can use bottom up design. Bottom up design mean we can use the system we have in our hand. Okay, actually in practicality bottom up design is used because we want to reuse the system we have in our hand. Okay, so we'll start from small components to big system, and real design uses both techniques, but bottom up design is more preferable. Okay, so what are the concluding remarks of this whole lecture? First, embedded computers are all around us. Okay, and many systems have complex embedded hardware and software. Embedded system pose many design challenges: design time, deadline, power consumption, etc. Design methodologies help us manage the design process. So design is varying depending upon the methodology and what we want from the embedded system. Okay, so that's it. Here are the references that I have used for making this slide. Okay, Google Images, Wikipedia pages, and YouTube videos of NPTEL by Dr. Shantanu Chaudhary, Department of Electrical Engineering, IIT Delhi. Okay, so that's it. Thank you. Have a good day.